guys, today we'll be learning about digital logic circuits. Digital logic circuits deals about electronic devices that you can use to implement your logic design. Now, you've been using AND or XOR and NOT in programming. We also have that in the hardware via these digital logic circuits. Most of the digital logic circuits sold are either TTL or CMOS, and they start with the code 7400 and 4000 for the CMOS. They are readily available in electronic stores. So for your prototyping projects and the like, you may purchase your logic gates. Now, in the digital logic circuits, there are only two values allowed. We have logic 1 and logic 0. Logic 1 is the same as your true value, and logic 0 is false. Sometimes we have these values, high versus low, or electronically, there is a voltage reading and there's 0 volt coming out or going in a particular device. Let, let's start with your AND gate. So if you can still recall your Java, AND gate looks like this. AND operator looks like that. And for the digital logic circuit, we have this symbol. This symbol is based on IEEE standard 91A 1991. They outline how the symbols look like and what are their behaviors. So typically a gate has an A input and a B input, and we denote the output as Q. This is called logical multiplication as opposed to arithmetic multiplication. So what is logical multiplication? Its truth table will tell you how a logical multiplication works. So taking the inputs A and B and the output Q will generate the truth table. A truth table is a summary of all possible inputs and their corresponding output. So to start, we have 0, 0, 0, 1, 1, 0, and 1, 1. What would be their output? The output is the following. That is coming from the rule that if you're using an AND gate, it will be 1 if and only if both of the inputs are 1. So if you can still recall your Java, it's the same principle. So there you have it, that is your AND gate. Let me just write its operation to be logical multiplication. Our second gate is the OR gate. And you usually see this in Java as the pipe symbol. Okay. So an OR gate looks like this. We also have two inputs for OR gates. No. And the same is true with its truth table. For the rule of OR gate, it says that if at least one of the inputs is 1, then the output is 1. Therefore, 0 and 0 will output 0. There's 1 here, so we'll get 1. We get 1. And 1 and 1, of course, would be 1. Okay. You'll notice, class, that for you to memorize it easier, for an AND gate, a 1, 1 gives you 1. For an OR gate, a 0, 0 gives you 0. So Those are the first two gates, the AND gate and the OR gate. Now, what is the operation of your OR gate? This is called your logical addition. Notice, class, that you always have one input there. There's no more carryover because it's a logical addition as opposed to your arithmetic addition. Okay. Another gate is the XOR gate or the exclusive OR. Some book would say XOR, but we'll use this three-letter word. Okay. Exclusive OR has the following symbol. It's like your XOR, I mean your OR gate, but there's a symbol for exclusivity, which is this one. You also have an input A and B and an output of Q. For its operation, it says that if you have opposite input, that is, if you have 0 and the other one is 1, that's the only time it will output 1. Therefore, the truth table would look like this. Because we have 0 and 1, 1, 1 and 0, 1. So that's your XOR gate. And what this is exclusive multiplication. Recall your rules, operation in discrete math. So having this, we go now to the last basic gate, which is called the NOT gate with the following symbol. Take note that it has only one input and an output. Therefore, the truth table should look like this. And for NOT gate, okay, if you can recall your Java, this is actually your NOT symbol. Okay. Its operation says that if the input is 0, the output is 1. 1, you get 0. And let me just change the color for this one. Sometimes it's called the complementation. Therefore, its operation is actually one's complement or complementation. Lastly, we can also write their symbol, their equation as Q is equal to A times B. Q here is equal to A plus B. And Q here is like A plus B, but with a circle to denote it's an exclusive multiplication. Sorry, let me correct that, guys. It's an exclusive addition, not multiplication. So those are the 4 basic gates. Now we can also have their complemented counterpart. All you have to do is insert a NOT gate at their output. So a NAND gate would look like an AND gate, okay, with a NOT in its output. But we can shorten this one with a drawing like this. Just place the bubble there, and there you have your Q. If we get our inputs A, B, and Q, input is the complement of AND gate. Therefore, this is 1, 1, 1, 0. So you just think of AND gate and then complement the output. Or it outputs 0 only if both of the inputs are 1. Let's skip or let's jump to XOR so that you can compare XOR and XOR. Take note of the N comes after the X letter and exclusive symbol. You have your OR, okay, and you have an input A and B, and you have your Q plus the NOT gate. So let me insert a bubble here. That's your XNOR. For XNOR's output, the same thing. You just complement the output of your XOR gate. So you have 0, 0, 1, 1, 0, 1, 0, 1. That would be 1, 0, 0, 1. Okay. Let me change the color so that it's easier for you to read. There you go. So that's your XOR. And before we jump to your NOR and the buffer, let's get their equation. The equation would be the same except that there's a bar on top. Okay. The bar on top there denotes your NOT, the NOT of the output. Therefore, for the NOT gate, Q is equal to A with a bar on top. Some books would use the prime symbol. It's the same thing. Okay, let's go to your NOR gate. For the NOR gate, okay, we have a symbol of your OR and the NOT in the output. You have A, B, and Q here. And the truth table would look like this. Since we have 0, 1, 1 as the output, we'll have the opposite, which is 1, 0, 0, 0. Therefore, it outputs 0 if at least one of your inputs is 1. And lastly, we call it buffer. The function of buffer is to strengthen the signal. Because you might be thinking, sir, what's the opposite of a NOT gate? If you have an input of A and an output of Q, you have the following. So if you have 0 here and 1, output is 0 and 1. So nothing happened. But the main purpose of buffer is to strengthen a signal. Okay, so and take note, when you connect two bubbles, they cancel out. Therefore, there's no bubble for your buffer. And those are your basic gates and their complemented counterpart. Now, for the equation of your NOR, it's also the same as Q is equal to A plus B with a NOT on top. For your XNOR, Q is equal to A times B and circle in between them. Okay. And finally, Q is equal to A. Now guys, some books would expand this as AB plus AB, but there's a bar on top. Okay. Let me just go back to your XNOR. This can be expanded as AB plus AB. You have a bar on top of the A, and the other bar is on the second term, which is on top of B. So these are your first 8 gates. Okay. Now, we can cascade gates to have a certain behavior. Okay, but that would be discussed in detail in the next lesson. Just for today, I'll give you a simple example on how to cascade them. Given the following, let's say you were asked to give the equation of the following. Sometimes the equation is given and you are to draw them. So this is just an example. Always label the inputs as A, B, and if you're done with B, you have to go on with C, and so forth. And our output would still be Q. Okay. So given the following figure, you are asked to find the equation of Q. This would be easy if you start from the output. So let me introduce another letter here. So A, B, C. This make it this point here would be D, and this point here would be E. Okay. From here, Q is an exclusive operation between D and E. Since our inputs are A, B, and C, we have to break down D and E. So D is actually A times itself because it is connected here. And we can group them. It would be more readable if you group them. And E is equal to B plus C. And that's our final answer. Q is equal to A plus exclusive plus the quantity of B plus C. Okay. Sometimes the equation is given and you are asked to draw the figure. Example of which is this one. Let me write it here. Okay. If you're given problems like this, start with the grouping symbols. So we have A and B here. And since this is addition, we'll use an OR gate. Okay. And the output of which is being multiplied with C. So you have here a multiplication. So that quantity is multiplied. So we'll use an AND gate. And let's label this C. And finally, multiplications comes first before addition, like in arithmetic operation. We're going to pull an OR gate and place it here. That would be Q, but an OR gate has two inputs since it's plus A. All we have to do is pull from A. So this is a connector symbol. It's like saying pulling from letter A. There you have it, guys. I hope you learned the basic digital logic circuits and how to cascade them. In our next lesson, you will be learning Boolean algebra, which will simplify these figures. That's all.